In this video, we're going to use first and second derivative information to graph this rational function. The algebra involved is going to be somewhat complex, technical, but the techniques that we used or identified in the previous video are going to be the same. So let's first take the first derivative of this function using the quotient rule. So we've done that, and notice that we have our dm prime minus n d prime over d squared, the quotient rule used. I'm going to refer you to the textbook, page 81, to see how this simplifies. Remember, what we're trying to do is set this derivative equal to 0. So let's get a simplified version of that in the next step. So we've got this fraction, simplified fraction for the derivative. We're setting it equal to 0. When we set a fraction equal to 0, the fraction is going to equal 0 where the numerator equals 0. The fraction is going to be undefined, and we're going to have to note that on our sign chart where the denominator equals 0. So the numerator of this fraction equals 0 where the quadratic in the numerator equals 0. So if we use the quadratic formula, we get the two places where the numerator equals 0 are these two x values, or approximate x values. So these two x values, 0.077 and 51.923, and the two places where the denominator is 0 are plus or minus 2. So let's put that information on a sign chart and find the signs of the derivative in the regions that those values define. When we test in these 5 regions, it's fairly difficult to find signs unless we use some computer help. So what we're going to do is we're going to learn in class how to use the MathCAD program to define or to give us the signs of the derivative in these 5 regions. I'm just going to, in this chart, put in the test values, which are -3, 0, 1, 3, and 55, and you can see that those are values here, 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 and here. And then I'm going to fill in the signs of the first derivative, which I obtained using MathCAD. So notice that on the sign chart where the denominator of the first derivative was 0 at -2 and 2, we put an infinity symbol above those two x values because the first derivative is undefined there, and at the two places where the first derivative was 0, where its numerator was 0, we put zeros on the sign chart there. So we have 4 of the values on our sign chart and 5 regions. And then we filled in the sign in each of those 5 regions, so the function is decreasing in these 2 regions. There was not a sign change across this place where the denominator is 0, which is also a vertical asymptote for the function. The function changes sign to increasing across here. However, it does not change sign across this other vertical asymptote. That is, the first derivative doesn't change sign across that, but then it does change sign over to decreasing across this last 0. So reiterating, the function is decreasing all the way up to this x value. It is increasing between this x value and 51, and then it changes to decreasing to the right of that. Now we're going to get the second derivative. The second derivative requires a little bit of algebra to simplify things before we put it into MathCAD to determine the signs. So we're going to go over in a little bit more detail how we get the second derivative that we're setting equal to 0. So here's our second derivative. Notice that we started with this as our first derivative, and then we're doing the denominator, derivative of numerator, numerator, and the derivative of the denominator is all of this, which is the chain rules used to get the derivative of the x squared minus 1, or x squared minus 4 squared. And then here we have the denominator squared. So we want to set this equal to 0, but before that we want to factor out a common term in the numerator. Notice that x squared minus 4 is common to this term of the numerator, and it's also common to this term in the numerator. And so we're going to factor that out. When we have a rational function, it's always going to be the case on the second derivative that we can do this factorization step. So let's set that up. So we factored out the x squared minus 4. That leaves this expression in the brackets that we will need to simplify, and we're going to be able to do some cancellation. This is going to cancel out with this and change the power of x squared minus 4 in the denominator to 3. Now, what does all of this in the brackets of the numerator simplify to? It simplifies to this. So our numerator simplifies to this cubic term, and we see that our second derivative now has this form that we want to set equal to 0. This numerator, though, presents a problem. It's difficult, very difficult, using algebra to find where cubic functions equal 0 with quadratics. We just use the quadratic formula. So setting the numerator of this derivative equals 0 requires that we use some computer techniques. We could actually use Newton's method that we learned earlier to find it. And when we do set the numerator equals 0, we find that we get x is approximately 87.86 actually. If you look in your textbook on page 82, you see a little bit more information regarding this. We're going to, in class, when we discuss this, see in more detail how we would find where the numerator equals 0. So we have that information now. We're going to put this x value and, again, x equals plus or minus 2 on the sign chart because the denominator is still 0 at plus or minus 2. And so we're going to now construct this sign chart for the second derivative. So here's the sign chart without the information filled in yet. Let's notice this about our second derivative. Since the denominator is cubed, this expression x squared minus 4 is going to change sign on either side of minus 2 and plus 2. So our second derivative will change sign on either side of its infinities, whereas here, notice, remember that we didn't have a sign change for the first derivative here or here, but we are going to have a sign change for the second derivative across that. So test values are going to be as follows. Let's just look at this sign of the denominator in all of these regions. So if we plug in minus 3 to this denominator, we're going to get 9 minus 4 cubed, or a positive denominator. If we plug in 0 to this denominator, we're going to get 0 minus 4 cubed, or a negative denominator. If we plug in 3, we're back to a positive denominator, and 100 gives us a positive denominator. Now we'd want to use some type of utility to figure out the sign we get in the numerator for plugging in these values, minus 3, 0, and 3. But so let's just fill that information in. When we plug in minus 3, the sign of the numerator is negative. When we plug in 0, we can actually see that because it's only at the minus 208 that remains, so we still get a negative. When we plug in 3, we get a positive, and when we plug in 100, we get a positive. So let's look at all that we've got now. So notice that this numerator sign, when we plugged in 3, should have been a negative right here. So here are the signs in the 4 regions: negative, decreasing, or I'm sorry, concave down, positive, concave up, negative, concave down, and positive, concave up. So concave down, concave up, concave down, and concave up. So let's put all of this information together on one sign chart so we can see the shapes in all the regions that we have. So we've got the sign chart filled in about these 3 or 4 critical values for the first derivative and 3 for the second, and there are actually 5 in total, so we have 6 regions. Let's put the dividing lines between the regions up. And now let's fill in the shapes, noting that we have vertical asymptotes for our function at 2 and minus 2. So here we have decreasing and concave down and going to a vertical asymptote. So that would be this shape here. Then we have decreasing and concave up, which would be this shape here, rising to the vertical asymptote on the left, but falling here where we have a relative minimum. Then it goes to increasing, concave up, going to this vertical asymptote. To the right of that, it is increasing and concave down, which is coming away from the vertical asymptote like this, and it's actually rising to a maximum here. Let's note back here that this was a relative minimum. This part here is a little bit hard to see. It then becomes decreasing concave down, which is this, which so it's decreasing and concave down in this next section, which is this shape. And then in the final region, it is still decreasing, but it is concave up, and so it goes like this to the horizontal asymptote. So if we fill this information in and draw the graph, which we've essentially already done, here's what we get. So we have drawn the vertical and horizontal asymptotes. Vertical asymptotes for a rational function occur where its denominator equals 0. So if we take the x squared minus 4 and set it equal to 0, we get its 2 vertical asymptotes plus or minus 2, which we've drawn here. Horizontal asymptotes in the case when the numerator degree equals the denominator degree, that's squared of the numerator, the denominator, is just the ratio of the leading coefficients, the coefficients of the highest degree term in the numerator and denominator, which is 1 over 1. So the horizontal asymptote is y equals 1. So we have that information drawn in on our graph. So I've drawn in the 3 sections of the graph. It's decreasing and concave down. In this section, it has a relative min roughly at the point 0.0776 or 7, and we'll see in class how to determine that point using computer techniques, how to find the y value at that point 0.077. It's decreasing and concave up on this side, and decreasing and concave up on this side. increasing and concave up on this side. And then I've exaggerated things over here. In this segment here, it's increasing and concave down. It has a relative maximum right here. It actually decreases on the right of that relative maximum, so the derivative goes from positive to negative on either side of this. And then it has this inflection point right here where the second derivative changes sign on either side of that from concave down to concave up on either side of that. Let's take a little bit closer look at what's happening here. The function's changing from increasing to decreasing with the concave down shape at that point. If it continued to be concave down, it would just keep going like this, and it would never level out to the horizontal asymptote. Instead, what's happening is it has a concavity change, and because of that concavity change about this point, so f double prime is changing from negative to positive, but that allows it to continue to be decreasing in this section, but gradually level out to the horizontal asymptote y equals 1. Alright, so we've completed the graph of this rational function. There are some portions of this that we're going to have to go over in quite a bit more detail in class to see how we do things like how do we set this numerator equal to 0 and find the places where this cubic numerator equals 0. How did we find this 77.86, such as by Newton's method? And in this case, the sign chart analysis for the second derivative. We'll need to go over that in more detail in class to see how we got that. We showed how we got it for the denominators, but want to be a little bit more careful about how we do it for the numerators. So that concludes this video where we constructed this graph, the graph of this rational function. And the rational function had a pretty easy to see shape and derivative analysis here, just a little bit more complicated in this region. But it was fairly complex what was happening at this x value 55 and at this x value 77. And so we'll need to look at that in a little bit more detail in class.